Okay, so this is problem 10.5, page 329. This doesn't exactly use calculus, but it is talking about using vectors to calculate the torque of a force acting at a certain distance. So the radius vector, or the torque arm vector, is negative 0.45 I plus 0.15 J. So you can see about 3 units this way and 1 unit that way, because this is 3 times that. Now the force vector, because the force is newtons, you would actually have to use a little care here in terms of the length of this, and really we're not so worried about the length of it, just to show you the direction. So you see it's negative 5 newtons in the I direction and positive 4. So it's not quite 45-degree angle. So, but this one's shallower. This is 1 and 3, and this is 5. It's 3 and 1. This is 5 and 4, so it's a little bit steeper. So to calculate the torque vector is equal to the cross product of the R vector with the force vector. So the R vector is the first one, and the force vector is the second one. So what we're going to do is we are going to do this cross product. So you would write this out completely as negative 0.450 newtons I plus 0.150 newtons J crossed with the force vector, which is negative 5.00 newtons I plus 4.00 newtons J. Now when you do a cross product, the way it works is you set up a determinant. It's a 3 by 3 determinant. And the top row are the I, J, and K unit vectors. And then you put in the vectors associated with R. I'll leave the units off right now. And then you put the units, the values in for F. And it's just two-dimensional. You've ended with that. So if you do the determinant of this matrix, you see these zeros are going to make it so the I and J parts go to 0. The only thing we're left with is K, and the way it goes is plus, minus, plus as far as the signs. So since the K vector is the third one across here, it's going to be plus. And then we do this 2 by 2 matrix, so we're going to have negative 0.450 times 4. And then we subtract this diagonal product. So it's going to be plus 1.5 times negative 5.0. And that whole thing is positive because it's also multiplied by the K vector. So it's going to be in the into the paper. So there we get. Let's get the calculator out, which I didn't get out of my bag. Okay, so we've got negative 0.45 times 4. And we got negative times a negative, so it's positive 0.15 times 5. So it's negative 1.05. So we get negative 1.05. The units are Newton meters, and the vector is k. So what this is telling us is that it's going to give us a clockwise rotation, because that clockwise is negative and counterclockwise is positive. And if we go back and actually look at this, if we actually were to break this force vector down into two components, you'd have a component like this, which is perpendicular to the moment arm, and you'd have this, which is parallel. And so this one is going to cause it to go clockwise. The other thing you would do is you would use the right-hand rule. And what you would do is you take your fingers along the R vector, and then you would curl your hand towards the force vector, and that would push your thumb into the paper, which would be would be negative. So into the Z direction here, that's negative, and coming out this way is positive. So the right-hand rule would say it's negative. Just looking at the component form of it, the component form of the force vector, you would say it's into the board. And finally, the sign of the cross product is negative, which also means that it goes in the same direction. So all three approaches give me the same answer. Hence, I believe that I have done this correctly. But I will look in the back of the book to check. So this is 10.5. So it says in the negative k direction, and the value, the actual magnitude is negative 1.05 Newton meters k. So that is correct.